presentation of Gabriele Sale, that is a researcher of the Istituto Italiano di Tecnologia. So, Gabriele, the floor is yours, and share your presentation.
Thank you.
It's okay, we can see.
Cool. Okay, so welcome back from lunch. I'll try not to be boring, to keep you awake. In this presentation, I'm going to talk about our work on the usage of big data and artificial intelligence, in particular machine learning, to design new materials, meaning semiconductors and quantum dots. Since this is supposed to be also a training course, I try basically to merge a didactical part with also a more scientific part in which I show you the results of our work during this IEMAP project. So, okay. This is the outline of the talk. I will give an introduction about semiconductors, quantum dots, and in general, the idea of materials discovery. Then I will show you our platform for the design of ligands for quantum dots. And then I will present our computational platform for the discovery of new materials, of new semiconductors materials, which consists in two modules. One is about mining of databases, materials databases, and the second part is about machine learning. And then I will summarize the talk. Starting from the introduction. So, of course, all of you know what are semiconductors. They are central in many technological applications. Basically, they are materials made mostly by these elements I highlighted in the periodic table, but not only, but these are the most common. The property that we are mostly interested in our group about semiconductors is their ability to absorb and emit light. So this makes them important for solar cells, LED, light-emitting diodes, displays, and a lot of other technologies. In this field, there is a constant need of improvement. For example, to avoid the usage of toxic elements, as Luca De Trizio mentioned earlier, because there are a lot of semiconductors which contain elements such as lead or cadmium, which are forbidden by the EU directive. Also, we want to try to make new semiconductors which have good properties, but they do not use, they use only elements which are abundant on Earth. For example, it would be ideal to replace what we have seen in the talks of yesterday, named as critical raw materials, to use only elements which are abundant and possibly also present in many parts of the world. And also we want to continuously improve their optical properties for various applications. So to do this, we need to do materials design, which is mostly what this talk is about. Quantum dots, we have heard about Juliette, a lot of nice things about quantum dots. Here I will focus more on the technological side. As Juliette said, this is a technologically important achievement as exemplified by the fact that the last year Nobel Prize was awarded exactly for the discovery of quantum dots. If we want to define them in two words, they are semiconductor at the nanoscale. So they are semiconductor nanocrystals. From the technological point of view, they bring several advantages over the macro semiconductors. They have a better, narrower emission, which makes them more ideal for displays because of color purity. They have a higher emission efficiency. Most importantly, they can be made in solution, so they are solution processable. This means that it's much easier to make them with respect to traditional semiconductors, and therefore the production cost goes down when we move to the nanoscale. They can also, since they are at the nanoscale, they can also be used for flexible electronics. However, they present some challenges, mostly the fact that on the surface, we see, since surfaces here are more important because we are at the nanoscale, on the surface we can have defects and traps that quench the emission of light, and this is detrimental for the application in which we need them to emit light. And there are a bunch of strategies to deal with this, some of which Juliette mentioned. Mostly we use ligands to passivate the surface trap. Also, they are more challenging to be characterized, but this is less important at the moment. We are interested in materials discovery or materials design, as I said. There are many ways to design new materials, 3 in particular, and they basically correspond to the paradigms of science. We can discover materials experimentally, just making them, knowing the rules of chemistry and physics. We go in the lab and we make them. This is a reliable way, but it's super slow and very expensive because we have to use resources to make material, man time to spend in the lab, etc. So we can't scan many of them. This is basically relying on the first 2 paradigms of science, which is theoretical science, so knowing the laws of chemistry, and empirical science. We can take advantage of the huge computational power that we have available nowadays, and we can discover new materials through computational discovery, which basically means running simulations on a huge number of materials until we find a material with the desired properties. The main drawback of this is that to do this we need a massive computational power, and even the modern supercomputers are sometimes not enough to scan all the possible compositions of materials. Or recently, in the last 10 years, we have what is called data-driven discovery. So we exploit the fact that nowadays we have a huge amount of data, such as materials databases, available, and we use them either to directly discover new materials by mining the databases, or by using them as a training set to train machine learning algorithms that can learn from the known data and predict the existence of new materials. And this third approach, which is based on what is called the 4th paradigm of science, is what the talk will mostly focus on. So moving to our approach for the design of ligands. Ligands, as Juliette mentioned briefly, they are important for quantum dots. First, because they make the quantum dot stable in solution. The quantum dot itself is not soluble, but we want to make it solution processable. So we need ligands to make the quantum dot soluble. Also, importantly, they passivate the surface traps, so they improve by far they are one of the main ways to improve their emission efficiency, and also they can be used to tune the band gap. To design ligands, we use this so-called funnel approach, in which we take a whole molecular database, which contains a huge number of molecules. We apply some selection criteria, which can be based on machine learning, on quantum chemical simulations, or even just simple chemical knowledge. We apply various screening criteria to find the molecules which are best suited to be used as ligands for quantum dots. This is in practice how our funnel looks like. We have a bunch of criteria. We start from the PubChem database, which is probably the most important database of molecules. It contains about 100 million molecules. We apply a lot of criteria to find the most suitable ligands, and we come up, and through these we can come up with the most apt molecule to be used as ligands. Now, I'm not going to go through each and every one of these criteria, just showing some examples. So the first screening criterion is simple. We take molecules which have only one anchoring group, and the anchoring group is the functional group which is apt to bind to the quantum dot. In this example, we have a carboxylate group. We call the rest of the molecule the backbone. By doing this, we already cut out 60% of the molecules, so we already reduce our pool of candidate molecules. In general, when a ligand binds to the quantum dot, we have 3 types of interaction between the ligand and the nanocrystal, among ligands, basically steric effects, and between the ligand and the solvent. Starting from the latter, the interaction between ligand and solvent is what confers the solubility properties to the quantum dot. The solvation property can be calculated quantum mechanically. It's not, say, complicated, but it requires involved computation. So this is not something which can be done on millions of molecules. So to do this, we to overcome this limitation, we use the structure property relationship, which is basically an archetype of machine learning implemented in the SCM package. The method is called Fast Sigma, and this is interfaced with the NanoCat package, which was created by Ivan Infante's group, and also some of the people that work in the IEMAP project. In this way, it is possible to calculate the solubility properties of a huge number of molecules and find and screen them to find those that are soluble in a given solvent. Concerning the ligand-ligand interaction, this is mostly about steric effect among the backbone of the molecule. And we use this protocol. We start from the SMILE format because all this huge amount of molecules are stored in this convenient SMILE format. We transform them back into a 3D structure of the molecule. We perform an optimization of the geometry and the linearization. And from this, we calculate this theta angle, which is what we call the cone angle. This is important because if the angle is big, means that the molecule is bulky and cannot the ligands cannot bind efficiently to the nanocrystal because basically they would hit each other and they would not bind efficiently. Finally, concerning the interaction with the quantum dot itself, we can calculate this using simple quantum chemical approaches. This is a fairly simple quantity to evaluate. Basically, it is the difference in energy between the quantum dot, or anyway, the inorganic surface with the ligand attached, the difference between these, and the situation in which the quantum dot and the ligand are far apart. This is the interaction energy, and it is the driving force for the attachment of ligands on the surface of quantum dots. By this, you have a general idea of the type of screening criteria that we apply to find the most apt ligands for the quantum dots. Moving to the project on semiconductors design and quantum dots. So nowadays we have big data available for materials. We have these databases which typically contain millions of materials, their structure, and also the calculated or experimental properties. This is a very valuable source of information which can be used. It can be used in two ways. The first way is to directly screen them and try to find materials which are appropriate for a given application, or we can use them to build a training set on which we train machine learning algorithms that learn the correlation between the material itself and some properties. And in this way, we can predict the existence and the properties of new materials. We adopt this supervised learning approach, which we have heard about today in the first talk. In short, we translate the material into a set of features, and we ask the machine learning algorithm to learn some properties of the material based on this set of features. The properties we are interested in for semiconductors is the thermodynamic stability, the value of the band gap, and whether the band gap is direct or indirect, because this influences whether it can efficiently emit light, and the masses of electron and hole, and there are a bunch of other properties. In this talk, I will focus mostly on thermodynamic stability, which is the most important property, because if a material is not thermodynamically stable, it cannot exist. This is the general framework. So we of our computational platform. It has an interface to databases and machine learning algorithm based on composition. And these two parts were developed as a part of the IEMAP project. From this, we can already generate a bunch of candidate materials. From these candidate materials, we can either feel lucky and try directly them into the lab, or we can make them undergoing a further screening, for example, by performing atomistic simulations, which give us some more accurate evaluation of their properties, or by screening them through synthesizability parameters, meaning predicting which which materials are easier to be made in the lab. So the part that we have developed so far is the one in this square, and it is the part which forms the basis for materials design, and it's what we develop within the IEMAP project. So the first part, the interface to materials database, we have built a Python code that is interfaced to basically the four most widely adopted materials databases, which is AFlow, Nomad, the materials project, and the Open Quantum Materials database. The user can select a bunch of criteria, and then the code retrieves the materials which fulfill those criteria. The criteria could be the chemical elements, for example, excluding toxic elements, the number of elements, whether the material has a direct or indirect band gap, whether the material is stable. This can be done only on certain databases. Or the user can even select the type of structure. For example, the user can select only material from these databases, can select only materials which have perovskite structure. The resulting materials are then stored in a Mongo database that can be either local on the user's laptop or on the cloud. For example, Amazon provides Mongo databases on the cloud. Once the resulting materials with selected criteria are stored, the user can either perform further simulations on these materials or perform more tailored criteria for filtering them and find the most appropriate materials. Or, as I said before, they can be used to train machine learning algorithms, about which I'm going to talk about. First, let me open a parenthesis about thermodynamic stability. As I said before, a material has to be thermodynamically stable to exist. There are cases of metastability in which a material is quite thermodynamically stable, but in general, it has to be very close to thermodynamic stability to exist. Thermodynamic stability means that a material is thermodynamically stable if it does not decompose into any mixture of other compounds with the same stoichiometry. In other words, more rigorously, the free energy of the material has to be lower than the sum of any possible combination of other compounds or materials with the same stoichiometry. Luckily, we don't have to scan all possible decomposition pathways because we use the construct of the convex hull. The convex hull is what you see in this image. In short, it is a plot of the formation energy or formation enthalpy against composition. The hull is the line which passes through the lowest lying points. And a material is, it can be demonstrated mathematically that a material is thermodynamically stable if it lies on the convex hull. Why I'm telling you this? Because this simplifies the problem a lot. Because given this convex hull construction, we are only interested in the formation energy to predict the stability, and this is a quantity which is much easier to be calculated and also much easier to predict than the whole thermodynamic stability. So we just need to predict the formation energy to ascertain whether a material is stable or not. We decided to use a machine learning algorithm which predicts the properties of materials based on just the chemical composition, meaning that we don't have to feed the structure to the machine learning. Surprisingly, machine learning is powerful enough to give decent, actually quite accurate predictions just based on the chemical formula. The property, to start, we predict the formation enthalpy, the width of the band gap, and the direct or indirect character of the band gap. As I said before, I will focus on the formation enthalpy in this talk. The drawback of using only the composition is that the accuracy is obviously limited, but we are interested in a screening tool that only gives us the good candidates to be tested in the lab or to be tested by further simulation, so it's good for us. And that some properties are not unique for the composition, so one can have polymorphs. We overcome this by taking for each composition only the lowest energy structure. There are big advantages. Well, first, it's easier to implement, but most importantly, once the user has the machine learning, the trained machine learning algorithm, it can directly predict new compounds. Whereas if one also involves the crystal structure to make the prediction, one also has to scan all the possible crystal structures and find the lowest energy one. This is not our case, since we have the machine learning, which basically creates a one-to-one mapping between the composition and the property. One can make direct predictions about the new materials to be tested. We used, here we talk about formation energy. We implemented the machine learning framework in a Python code that uses the scikit-learn library. We started from the materials project. We took all the compounds which display a band gap, so they are semiconductors. We store them in a Mongo database. And then we filter them for those compounds that have at least one of these elements in green, which are typically cations, and one of these elements in violet, which are typically anion. We end up with about 19,000 compounds. We use 17,000 of them for training and test, and 2,000 for validation. Now, in the machine learning world, the words testing and validation are used interchangeably, and we have seen this in the first two talks of today. To be clear, these 2,000 materials are excluded from any type of fitting. So the machine learning algorithm does not see these 2,000 materials until we make the prediction. So it's what Serena Donofrio called validation and what Marco Catillo called test. So these are data which the machine learning does not see at all. They are used for prediction. We need to use the machine learning. We need to translate the chemical formula into a set of features, which is a language the machine learning understands. And we do this by taking the statistical quantities of the properties of elements. For example, electronegativity, atomic radii, ionization energies. We take this and we calculate the maximum, minimum, average, and standard deviation for each chemical formula. And based on that, we predict the formation energy. We tested many machine learning algorithms, and the one called extra trees gave the best accuracy. I'm not going to explain what is extra tree, but I'm giving you the name in case you're curious, you can look it up. And these are the results. So on the left, you see, so the plot is the formation energy predicted by machine learning on the x-axis, and the, say, true formation energy, that is the one calculated at the quantum mechanical level. In the fitting, all the points lie on this green line, which is the perfect prediction. But this is the fitting, so these are the data on which the machine learning is trained on. It's not assumed that they lie on this line, but they do in our case, whereas for prediction, they are a bit scattered. But you can see that most of them lie on this green line. There are a few outliers, but remember that in this plot on the right, there are 2,000 points. So most of them, the great majority of them, lie on this line. The mean average error is 0.1 electron volt per atom, which may not be good enough to make a perfect prediction, but it's good enough to apply screening to materials to exclude those that are certainly unstable. And also, it's pretty impressive if you remember that these predictions are made just based on the chemical formula of the material. There are no other information are fed to the machine learning algorithm. So in summary, with this the IEMAP project, we developed computational platforms which are data-driven and based on machine learning that basically build the foundation to data-driven materials design. We targeted new ligands for quantum dots in a funnel-like approach to find the most apt ligands for quantum dots out of basically all known molecules, because the PubChem dataset contains all the molecules which are known. Also, we built a platform to screen materials databases and machine learn their properties that are relevant for applications in the field of semiconductors. I would like to thank Liberato Manna's group, the whole group which participated into these projects within the Italian Institute of Technology. Ministero dell'Ambiente e della Sicurezza Energetica, which, as far as I understand, fund this project through this IEMAP project through the Mission Innovation Italy, and also the Cresco people for providing computational resources and support. And Cresco is provided by ENEA. And thank you all for your attention.
Thank you, Gabriele, for your very interesting presentation. Are there any questions from the audience? Yes, there is a question from Marco Capillo. Please, Marco.
Yes, I have a question. So you said in your talk several times you can predict completely new materials, right?
Yeah.
In my knowledge, I don't know algorithms. I mean, I know algorithms that from a material you can get properties of a material, but the other way around, so predicting a new material, do you, I mean, in your knowledge, do you know algorithms or procedures to really predict new materials from machine learning? Or,
Well,
I mean,
yes.
or you can elaborate more on this.
Yes, there are examples in literature, but what I mean is the following. So I explained this convex hull construction, right? Let me find it. What's that? So we know that materials that lie on the convex hull are stable. We predict the formation enthalpy. So once we have our machine learning algorithm that can predict the formation enthalpy, now imagine that our algorithm was perfect and we could predict exactly the formation enthalpy. We just scan all the possible compositions and build a convex hull for each of them. And if a composition lies on the convex hull, it means it's stable. And if that composition, so that material stoichiometry was not known, it means this is a new material.
Okay.
This is done in literature. Typically, they don't do it with machine learning based, composition-based machine learning. They do it with structure-based machine learning, but that's much more complicated. There was a very famous paper last year by Google DeepMind. They did exactly that.
Okay.
Does this answer your question?
Yes, yes, yes.
Okay.
Thank you.
Thank you.
So thank you, Gabriele, for thank you again for your presentation.
Thank you.
Closes the set of presentation related to work package 1. And now we move to presentation of work package 3, that are materials for electrolyzers. And this presentation is given by the group of CNR of Palermo. And Leonarda, the floor is yours. Yes, your presentation is available on the Teams. Okay.
Okay. So thank you very much, Simone, and good afternoon, everyone. It's my great pleasure to take part in this session on materials for electrolyzer. I am Leonarda Liotta, and today I will present with my colleagues Francesca De Ganello and Chiara Aliotta our results on methodologies for electrocatalyst design in the field of emission innovation, in particular in the IEMAP platform. We work at the CNR Institute for the Study of Nanostructured Materials, and our institute is in Palermo. Sorry. Okay. So briefly, today we will present at the first, I would like to introduce the ISMN and the research activity that we carry out in Palermo. Then the issue related to the CO2 and the solution that we propose in our laboratory. Then we will speak about materials for electrolyzer with a special focus on perovskite oxide. We will present results about the synthesis, X-ray characterization and ritual refinement, electrochemical processes investigation by impedance spectroscopy. Then the data recorded will be presented in a data sheet in order to be uploaded in the Italian Energy Material Federation platform, and we will conclude with the conclusion and the perspective. Just to introduce, we are in Palermo, and this is our unit at the Institute for the Research of Nanostructured Materials. The institute is constituted by three different main branches, one in Bologna, the other in Rome, the other one in Palermo. Different research fields are developed at the ISMN, and in particular in Palermo we work on catalytic processes for environmental protection and energy sustainability. And in this field, we have developed the different types of materials to be applied to the ENEA project. This is our research team working in the topic energy and environment. Here you can see our facilities. We are able to prepare different types of materials in the form of different powders, or eventually also in the form of structured catalysts. Then we test our materials for energy application in specific sample tube, where we carry out different catalytic tests in different atmosphere depending on the topic. In this slide, you can see also our capacity to prepare a monolithic catalyst. So this is these are examples of different monoliths, and that we can prepare directly by the deep coating technique. The powders is deposited over the cordialite wash coated material. Such material are analyzed by different techniques like scanning electron microscopy or just simply optical microscopy in order to investigate the different morphology and the distribution of the powders. Moreover, in our institute, we have different facilities and several instruments that we use in order to characterize our powder materials. So we have two different diffractometers. We have a ball milling system that gives us to crush our powders and to prepare proper slurry that we can use in order to deposit our active materials over cordialite, over slab, depending on the application. Moreover, we can analyze the surface of our materials by X-ray photoelectron spectroscopy, determine the morphological and textural properties by nitrogen absorption-desorption, characterize the thermal stability of our materials by TGA and DSC, and of course to register the impedance spectroscopy impedance spectroscopy to analyze our materials. Here you can see some different gas lines that we use in our laboratory in order to investigate our catalytic materials, especially for the CO2 abatement and for the conversion of CO2 in valuable products. Moreover, we carry out also several types of reaction for gas abatement. But just to focus on the field that is very well related to the IEMAP project. So our expertise is just related to the synthesis and characterization of different types of material that we investigate in order to reduce the CO2 overproduction due to the fossil fuel use and in order to reduce the greenhouse gas effect, transforming the CO2 in hydrogen and other valuable products such as chemicals, materials, and fuels. In order to do this, we try to reduce at the minimum the CO2 emission and therefore to reduce the carbon footprint for energy production. How we do this? From a thermocatalytic point of view, we investigated the conversion of methane and CO2 that are the most abundant greenhouse gases through the dry reforming of methane in order to convert such gases into methanol, fuels, hydrocarbons, and oxygen. But also we work on solid oxide fuel cell and solid oxide electrolysis cells that represent really the focus of our investigation in the field of IEMAP, the IEMAP project. While solid oxide fuel cells are able to co-generate electricity, hydrogen, and heat, in the case of the solid oxide electrolysis cells, we have developed in particular the design synthesis of new cathodic materials able to activate and to reduce the carbon dioxide to CO or to CO and hydrogen if we fuel CO2 and water at the cathode, in order finally to produce syngas, that is the starting material for the production of molecules with added value.
In order to use a convenient material in the electrocatalytic cathodes, we selected a class of materials that is very well known and are perovskite oxides. Perovskite oxides have the main structure ABO3, where A is the A site and is usually occupied by larger cations, like for example lanthanum, and B sites are occupied by smaller cations, like for example iron, and are coordinated by 6 atom oxygen atoms. And then we have oxygen sites that are exactly that coordinates the A site and B site cations. They can be doped and they can have different composition. They can be considered multi-component oxides and multifunctional materials. Besides as electrocatalysts, they can be used in general for other types of catalysis, heterogeneous catalysis, like as sensors in metal-aid batteries, as dielectrics in connectors, as electrolyte materials, and also magnetic materials, to cite the most important application, which is our research strategy, is to dope the perovskite and explore different synthesis methodologies. So a doping strategy and a synthesis strategies. Both the methodologies that we use are based on citric acid. One is consists in a fast crystal growth, which is solution combustion synthesis, and another is a slower crystal growth and is a more typical salt gel inorganic synthesis. I will describe this method in a few minutes. Solution combustion synthesis is essentially a redox reaction between fuels and reducers and oxidizers, so a fuel and an oxidant. But this redox reaction occurs in the presence of metal cations, producing a flame that can be controlled depending on the composition of the combustion mixture, and it's more or less like the fireworks. So, but we are interested not only in the beauty of the flame, but also in the in what we get at the end of the fireworks, which is a powder. That powder for us is very valuable because it's our final product. Preparation procedures is very simple. We have a so-called combustion mixture that can be also composed by solid materials, not only materials in solution. And we have, for example, a dispersion of silica, for example, together with other materials. So we have this combustion mixture. We regulate pH if necessary for the and then we insert all the main components: fuel, oxidants, metal cations. And we evaporate the water, we take out the water until a gel network is formed. This gel network is very important because if the gel network is well constructed, well done, we have a good combustion and a good product. The gel has the function of keeping all the components interacting each other in that position during the very fast combustion process that is activated at 200 degrees on the hot plate, and in few seconds produce the as-burned powder, as you can see from the picture, that eventually can be thermally treated and to obtain calcined powder. In the case of perovskite oxide, this is the case because perovskite oxide needs high temperature for crystallization. The most important parameter that we can optimize and control in the solution combustion synthesis is the fuel. The fuel has a triple role, so of course it is a reducing agent, is a chelating agent because it should form metal cations networks in the gel, and then has also the function of a microstructural template and influences the microstructural properties of the final material. The fuel can be any organic with these three characteristics. For example, sucrose, cellulose, or a polymer. And the final powder depends a lot on the type, on the amount of the fuel, selected fuel. Regarding the amount, we have two parameters very important. One influences the redox environment during the combustion, which is the reducer to oxidizer ratio. The other influences the chelation of metal cations and the formation of the network, and also the porosity, because when we use a lot of fuel, we have too much spaces in the network during the combustion, and we could have positive or negative depending on the materials. But for sure, it will affect the morphology, the homogeneity of the powder and the final properties. If you want to know more, you can read this review of some years ago. And the other methodologies starts also with citric acid. We have a solution. We have pH, high pH, and we have also of course, the metal nitrates as a starting point. But the gel formation is low, and then from the gel formation, from the gel to the perovskite powder, we have a slow decomposition, first heating at 180, then drying at 200, and then the treatment at 900. So this slow transformation allows to control very well the particle size, to reduce agglomeration of nanoparticles, and to obtain excellent chemical homogeneity, like usually is obtained in sol-gel methods. Which are the samples that we have prepared, the type of samples. They are perovskite oxide, and and we started from one basic structure, which is a lanthanum ferrite with strontium, 40% of strontium at the A site, which is fixed, and 20% of cobalt at the B site, which is also fixed. What is changing? Is changing the amount of iron, because we dope with nickel, 10% molar of nickel or 10% molar of copper that replace the iron side. And we check the effect of the B-type dopant, nickel and copper, also in the presence of fluor at 10% molar fluor at the ore site. Fluor has an indirect effect on the mobility of the oxygen vacancies. So it does not increase the oxygen vacancies, but increase the mobility of the oxygen vacancies, attracting the metal cations and in the perovskite. The other strategy, as you know, is the synthesis strategy. So we prepare the same compound, the same composition, but using solution combustion synthesis or sol-gel synthesis, citrate acid, so sol-gel synthesis. All these materials, these powders should be characterized, and the first characterization tool that we use is the investigation of the structure by X-ray diffraction, powder X-ray diffraction. To do that, you need first qualitative characterization, and we use an inorganic structural database where you can find the information on the design stage and on the analysis stage. Design, because you have all the information on the structure of the compounds that we know in the world, and we have also the access to the source and the water, so you can have information, you can prepare graphs, you can compare your pattern with the literature one. So it's a very powerful tool for the qualitative analysis. And then you can get information for the quantitative analysis by residual refinement. We use GSAS2 program. It's a very user-friendly program, and from that we can select by qualitative analysis a reasonable model starting structure that is close, resembles our pattern, and then we can refine to minimization of some functions, refine the data and find try to find check if this model is okay or not. Of course, it is okay, so the fitting is good, the graphical fitting is good, and is reasonable. The parameters are reasonable. So we can get phase composition, for example, cell parameters, crystal size, microstains, so chemical, microstructural and structural characteristics. Of course, to perform a good Richter analysis, we need high resolution X-ray diffraction to have a reliable analysis.
Well, in Mission Innovation, we brought our experimental approach to implement data as metadata. Our expertise in doing materials is based on synthesis procedures, but also in a deep characterization of the materials. We studied materials for CO2 electroreduction. As a consequence, our material must be structurally stable. They have to be able to absorb CO2, but also as electrocatalyst must be exhibit ionic electronic conductivity. Well, in our labs, we are able to test all these properties by performing X-ray diffraction associated with the Rictveld analysis method, X-ray photoelectron spectroscopy, CO2 thermogravimetric analysis, and finally, electrochemical impedance spectroscopy. As it introduced before, in Mission Innovation, we started two different procedures, synthesis procedures and doping strategies. For evaluating the effectiveness of these different type of strategies, first of all, we have to verify if our materials are formed during the synthesis. Well, X-ray diffraction tell us that our samples exhibit a perovskite oxide phase with rhomboedral phase for all samples, except for the co-doped samples, co-doped with copper and fluorine and synthesized by both synthesis methods. In these cases, a secondary phase is present as strontium fluorine, very little, 1 weight %. X-ray diffraction associated with the Rictveld analysis gave us information about cell volume, parameter cell. This is very important because through the evaluation of these parameters, we can evaluate if the dopants were inside the crystal structure. Well, X-ray diffraction is a technique that gives us information on a long range structure that is bulk information of the materials. But for CO2 electrocatalytic activation, the material must be interacted with the CO2 in-gas phase. So it's very important to study also the surface of the materials. In our lab, X-ray photoelectron spectroscopy gives us information about the first layer of the surface. For example, we can see here that the co-doped samples prepared by SCS exhibit on the surface strontium fluorine, whereas the same sample, the same composition, I mean, but prepared by citrated, not. XPS gives us also information about oxygen contribution, surface or lattice contribution. In this case, we have a similar response by changing doping, but also the synthesis procedures. Materials must be able to chemisorb CO2. In our lab, we are able to test these properties by thermogravimetric analysis in CO2 at different temperatures, and also by changing the cycle of chemisorption and desorption. We report here the data for the samples differently doped and also prepared by solution combustion synthesis and citrated assisted method. In both cases, the co-doped samples exhibit the highest CO2 chemisorption capability. In general, material composition and morphology affect these properties. Finally, in our lab, we are able to test the electrical properties of the materials. To the scope, we have to prepare bottom cell. A bottom cell formed by the three key elements of a solid oxide electrolysis cell, that is the electrolyte component, the cathode, and the anode. In our lab, in details, we prepare an alpha cell bottom cell, that is, we spread on both faces of the electrolyte material the same electrode materials. For this type of measurement, we start with the synthesis of the electrolyte powder. We selected samarium doped cereal because it is one of the best ionic electrolyte conductors for solid oxide cells. We prepared this material by solution combustion synthesis and treated the material at 500 degrees. By using a die of 30 millimeters and an hydraulic press, we prepared the green pellet, this one, and the green pellet were sintered at 1250 Celsius degree for 10 hours in air. The final sintered pellet was spread with the electrode material. The electrode material was prepared by the formation of a specific ink formed by perovskite powder mixed with polyethylene glycol and ATOH. Before we spread the ink above one of the surface of the pellet, we performed the pre-treatment in air at 160 Celsius degree. After this pre-treatment, we spread the other face, again the same pre-treatment. Finally, we treat the bottom cell in air at 900 Celsius degree for 2 hours. In this way, we have produced our membrane electrode assembly necessary to perform electrochemical impedance spectroscopy. This is our instrument, a Metron Autolab impedance analyzers equipped with a probostat cell from Norex for testing at a higher temperature. Our tests were carried out in pure CO2 at OCP, and the data reported here is a Nyquist plot where impedance is here we have the real component of the impedance, and here the imaginary component of the impedance. These are a series of semicircular. Each semicircle corresponds to a specific circuit elements. By modeling this data, we can obtain information about the area surface resistance due to the ionic electronic transport of the material, but also the reaction transport, heterogeneous reaction above the materials. These properties is influenced by the composition, we can see here. Well, all these data were collected as Excel data sheets. These Excel files were uploaded in a IEMAP platform and easily converted to JSON files. Finally, our contribution in mission innovation was by developing doping and synthesis strategies which are effective in producing perovskite oxide powders with different CO2 chemisorption properties, structural properties, and electrochemical properties. A key point of our approach is the correlation between structural and functional properties, because this type of approach is extremely useful for the assessment of new and innovative materials for solid oxide electrolysis cells. Thank you.
Thank you. Thank you, Leonarda, Francesca, and Chiara, for your presentation. And now the floor is open for questions.
Can
Yes,
you?
of course.
Is it okay?
Yes. Okay.
All right.
So, Lucia, the floor is yours.
All right. So I will start. So with this talk, we go back to materials for photovoltaics. We had other talks yesterday in the morning. So now we are back to perovskite solar cells, the activities carried out within the IEMAP project in ENEA. I'm Lucia Mescaldo, I'm senior researcher at ENEA with long time experience in photovoltaics, starting from silicon up to novel approaches. And since, oh, it's not going. All right. Since March this year, I'm head of the Innovative Devices Lab in the Solar Photovoltaics Division, Energy Technologies and Renewable Sources Department. As for our location, we are located in Portici Research Center near Naples. In our laboratories, we work on several photovoltaic technologies. We carried out R&D activities on silicon heterojunction solar cells, perovskite solar cells, monolithic perovskite silicon tandem solar cells, organic solar cells, agrivoltaic concepts based on thin films, and also characterization of encapsulants for eco-designs of photovoltaic modules. In this talk today, I will focus on perovskite solar cells and in particular what we did within IEMAP project. But before going into the core of the talk, let me just give you a context, a broad context about the numbers of renewables and of PV in particular. On the left side, the figure shown on the left side shows the evolution of annual renewable energy installations. And we can see that photovoltaics plays a big role and is the fastest growing technology, is the yellow part in the bars. On the right-hand side, we see the evolution of the cumulative installations of photovoltaics in the world. And we see now really important numbers. So in 2023, we reached overcome 1.5 terawatt cumulative installation. So photovoltaics is now really, we can say that photovoltaics is set to be a key player in the global transition towards clean and sustainable energy systems. As for the technologies, the market is dominated by crystalline silicon. The crystalline silicon market share is currently around 97%. This is also because silicon has been around for quite a while. For many years, and we can see in the another chart here that other contenders came into play recently, and so perovskite solar cells are now emerged as a very promising technology, not only as an alternative to silicon, but actually for going together with silicon, both as an alternative approach, but also together with silicon in tandem designs, where perovskite and silicon are applied together and can go beyond the limit, the efficiency limit of a single junction solar cells. Now, with this context in mind, we can really start with what we did within the IEMAP project. So this is just an introduction, but I can go very quickly because yesterday I've seen that there were already some introductory slides in another talk. Perovskites are any material with chemical formula ABX3 with the crystal structure like the mineral perovskite, the calcium titanate, the mineral discovered in the Ural Mountains in 1839 and named after the mineralogist Perovskite. The materials that are used in photovoltaics are metal allied perovskites. On the right hand side, we see the structure of the archetypal material, the methylammonium lead iodide, with the methylammonium cation occupying the site A, lead occupying site B, and the X site occupied by anions, in this case iodine. But more in general, the metal halide perovskites in PV present many other combinations in the sites A and B, and also several options for the anions of chlorine, bromine, iodine. The main properties relevant for PV are the strong absorption of the material, the sharp absorption onset, which means also excellent electronic properties enabling high open circuit voltage in the solar cells, and the band gap tunability in the visible range. And now let's go to the solar cell architectures. Until now we have seen something about the material, but what about the solar cells? Let us start with the silicon solar cells so that we can compare the designs. For silicon solar cells, there are several options, several designs. Here I'm showing the silicon heterojunction design, which is one of those that we are investigating in our lab. We are talking about wafer-based solar cells. So we have silicon wafers with the electron transport layers and hole transport layers on the two faces of the wafers for collecting separately electrons on one side and the holes on the other side. So it's a selective charge extraction design. Similarly, with perovskite solar cells, we have structures like what we have seen here. So with the charge transport layers on both sides of the absorber material. But one main difference we already can see here is the thickness of these solar cells. One is, in case of silicon, is a rather thick structure. It's based on a wafer with let's say now it's getting around 150 microns thick in the commercial designs. While with the perovskite solar cells, we are talking about thin film architectures. So we have thin film stacks on a substrate. But just for completeness, I want to mention that there are also mesoscopic designs, which I will not discuss here, as we stick with the planar design in our activities. There are many ways of preparing perovskite films. The main ones are solution processing approaches, and we also started with approaches like these in our labs. So here is a picture, I'm showing a picture of our fabrication lab with several glove boxes. And we moved from the archetypal methylammonium lead iodide composition to triple cation and mixed halogen compositions. And within the IEMAP project, we collected many of the characterization. We did lots of characterization of the materials and collected the fabrication procedures and properties of the various layers and uploaded them into the IEMAP database. Together with the activity on the perovskite absorber, we also worked a lot on the other materials in the structure. We have seen that here we have several charge transport layers, buffer layers, TCOs. We explored several of these materials prepared by chemical or physical methods in our labs and fully characterized. About these other materials, what is really relevant is that they should be transparent and have some electrical properties that are appropriate to their role. So what we did is doing transmittance, spectra studies, work function investigations, and so on. And all these properties and fabrication procedures for all the layers were collected and uploaded again in the IEMAP database. And this was a sort of a start in our activities, where a big role was played by the investigation of the optical constants of the layers. And we now have a sort of a library of all the optical constants of all the materials we prepare in our lab, which helps us also, which allows us also to do optical simulations of the solar cells that we make. For example, I'm showing a comparison of the experimental external quantum efficiency of the solar cells prepared in our labs versus the simulation of the absorptance in the perovskite films. And together with this comparison, we actually also could investigate the parasitic absorption losses by the other supportive layers in the structure. And this can be useful toward device optimization. Other interesting things are the possibility to simulate optical properties of the materials, like the transmittance of the perovskite films under preparation, so that we can compare experimental and simulated transmittance of the layers. And I can show you afterwards in the slides that this helps us in a fast-track optimization of the material. So we started with the solution-based method, but the key challenge with perovskites is also moving towards larger scale, so let's say to upscalable methods. So there are upscalable methods that are solution-based, but also upscalable methods that are vacuum-based. Also considering what we have available in our lab, we decided to move towards vapor phase methods, and together with that explore also hybrid methods that combine evaporation with the second step that is still solution process based, but with the potential to go to upscalable solution approaches, also as in this second line and this figure, one of these other techniques. So what are the advantages of vapor phase methods? Evaporation is a well-established industrial technique where large area is feasible, as it has already been demonstrated. It is possible to obtain high qualities in films with high purity and uniformity over large area. It is possible to obtain conformal substrate coating. So in case we have texturing, you really have a conformal coating. It's a solvent-free fabrication process, so intrinsically it does not use toxic solvents, and it is in principle possible to control the composition of what you are preparing. There are concerns, though. The control of sublimation of organic salts is critical, and reproducible procedures need to be established. Here in the figure, I'm showing our facility in ENEA. We have evaporation system with 4 fusion cells that allows for uniform deposition up to 10 by 10 centimeters square. This is integrated into a glove box. And this glove box is in line with all the other glove boxes that I've shown in the other pictures before, so that also for completing the full solar cells, one can keep the samples always in controlled atmosphere. So with our system, the facility allows for partial automation and also for use of the full process data saved real time in internal database. This is very important for reaching a really reproducible process and fabrication method, because one can have knowledge of what is going on while monitoring main deposition parameters. At the moment, this is saved in an internal database, in the machine database, and we can play with what is saved in just by hand, let's say. But meanwhile, colleagues from the IEMAP platform are developing a way for moving from machine database to the IEMAP platform, and preparing also a custom program to enable real-time monitoring and storage on the platform, and a Jupyter notebook to facilitate data analysis. So querying data, generating charts, performing data analysis tasks. So this is under development right now. This is an example of what one can do by monitoring. So one can control what is going on about the stoichiometry of the films under preparation. So parameters that we should look at and really monitor are the pseudo rate near the sources, the inorganic and organic sources, and the pseudo rate readings near the substrates. I don't go into details because you here see many curves, but just monitoring this, one can keep track of what is going on and adjust the conditions. Another parameter is really important to check, especially when dealing with organic precursors, is the pressure in the chamber. And so we can see here, for example, in this curve in the middle, in this graph in the middle, that when there is more organic precursor, the pressure is higher in the chamber, so one can adjust the conditions by looking at all these parameters. So what is important is always work with measured amount of precursors and monitor pressure and pseudo rates. And here I'm showing a slide where we can see how the transmittance measurements can be helpful while controlling the stoichiometry or the materials under preparation. So here there are examples of transmittance spectra measured for different samples prepared with different condition of different deposition condition, like the source temperature or the quantity of precursors in the crucibles. And so we can easily see that by comparing experiment and simulation, it's clear when we are really off stoichiometry or close to stoichiometry. And we have reached a condition where the real deposition rate for lead methyl ammonium lead iodide is around 1.1, 1.3 angstrom per second when starting with the deposition rate of lead iodide alone, that is around 0.6, 0.7 angstrom per second. These numbers are in agreement when we consider molar masses and densities of materials. And we are now exploring the possibility to grow high quality materials also at higher deposition rate. Now moving to the hybrid two-step method. What is this method? Here we prepare a template of just inorganic component. So we evaporate the inorganic salts, in this case lead iodide, in the deposition systems that I showed before. And then we move out of the deposition systems, and by spin coating, we apply the organic salts via a solution process. So in our case, spin coating of methyl ammonium iodide in alcohols. With this approach, there are no more issues with the evaporation of the organic precursors. This is an advantage. We can still use green solvents, so it's okay for the environment. Still, the compatibility with textured substrates is maintained. And as for the scale-up, there are options available. Of course, not spin coating, but from spin coating, one could move, for example, to slot die. The main variables in this case, I'm now talking about MAPI, but this could be then generalized to other compositions, is the deposition rate of the template, the inorganic template, then the concentration of the organic salts in the solution, the annealing conditions, and possible other treatments. And we devised a way for a fast-track optimization of this two-step method, again by using fast transmittance measurements. So here it's a workflow of what we did. So there is the top part is the evaporation, is the fabrication stage. The bottom part is the characterization and cross-check with simulation. So we start with the evaporation of the inorganic template. We can prepare up to 9 samples all equal to each other, and then just move one towards the characterization stage and check what is the thickness of this layer, and all the others move to the spin coating stage and annealing. And in this case, we can check, we can test different, we can vary all the other parameters like concentration of the methyl ammonium iodide, annealing, and so on. And so the other, all these films go then to the fast characterization step for the transmittance measurement. The comparison of transmittance spectra with the lead iodide alone and the full material allows to get an idea of the stoichiometry, because we know what to expect as a ratio of the two layers, always based on densities and molar masses. In addition, by looking at the interference fringes, if we observe weak fringes, like in the figure that I'm showing here, we know that there is some top residue, for example. So there are many, there is a lot of information coming from this quick test. And with a coarse tuning, we can go over and over this loop, and then when we are much more confident on the material, we go on the fine tuning with additional characterizations like XRD, ellipsometry, dark plot, photoluminescence, and so on, and obtain finally optimized sample. And here I'm showing just a few figures related to the optimized samples, so some results on the films. So on the top line, we can see results related to the two-step approach, hybrid approach, and the bottom line, the co-evaporation approch. So we see some properties like photoluminescence, XRD, and optical results. So just also to give you an idea what are the facilities that we have here in our lab. A micrograph, SEM micrograph here. And I'm also showing this other SEM micrograph of a deposition on textured substrates. This is a typical morphology of crystalline silicon, textured crystalline silicon used in photovoltaics with pyramids in the micrometer range. And you can see the coverage is conformal when we deposit by collaboration the perovskite film. Now moving to the solar cells, the main characterization facilities we have here are AAA class dual lamp solar simulator, class A xenon lamp solar simulator, or working on rather large areas, and a setup for external quantum efficiency, reflectance, and internal quantum efficiency measurements, both on designs with wafer-based design and thin film-based designs. Within the IEMAP project, we also acquired another characterization system, a platform, and only one electro-optical characterization platform that can be applied to both materials and solar cells. It's a modular system. In the pictures on the left-hand side, we can see there is a temperature-controlled stage where one can mount the sample. An enlargement is on the bottom right-hand side, where we can measure photoluminescence, electroluminescence, pulsed electroluminescence, transient photoresponse, impedance spectroscopy, dark and light JV curves, with no need to move the sample. So, which makes things really fast. At the same time, there is another part with the class A multi-LED sun simulator and light soaker that allows to work on areas up to 30 by 30 centimeters squares, where we can arrange some environmental chambers with custom sample holders, the figures on top here. These are detachable chambers that one can bring into a glove box for mounting the samples and then close them, for example, and then move them to the lab for characterization. And this is also equipped with a multi-channel suite for fast solar cell characterization, which allows us to do simultaneous JV curves acquisition and maximum power point tracking of the devices. This makes it possible to have fast-track initial characterization of the cells, but also stability investigation of different devices all at the same time. And here in this slide, I'm showing just several PIN and NIP solar cells that are under screening with various designs. These are pictures of lab scale designs implemented in our lab. And here also some results about the NIP solar cells with co-evaporated MAPI, methylammonium lead iodide, and the evolution that we with subsequent patches down here. So as long as we understand better and better the deposition conditions, then we improve the quality of our devices. And with this, I just stop here, and I want to thank the organizers and you for your attention.
Thank you, Lucia, for your presentation.